Let's get started. In the rest of this module, we're going to cover what ownership means. We'll talk about how Rust's system of ownership differs from some other languages, such as manual memory management in C and garbage collection in Ruby. Then we'll get into some code with the string data type. We'll show how you can move ownership from one function to another, and how you can clone data to duplicate it and thus have two separate owners. We'll finish up by giving you an exercise to try on your own before you watch the next module, in which we'll discuss possible solutions to the exercise. So, what is ownership? Ownership is Rust's strategy for managing data in memory and preventing common problems. Every chunk of memory must have one variable that is the memory's owner. The owner is responsible for cleaning up or deallocating that chunk of memory. This cleanup happens automatically when the owner variable goes out of scope. The owner of data is also who is responsible for deciding whether that data is mutable or not. Imagine a piece of data as a dish of food that Jane owns. She brings it to a party to share with everyone. As the owner of the dish, she's responsible for cleaning up any leftovers and taking the dish with her when she leaves at the end of the evening. One problem that ownership solves is that leaving the dish around the host's house would be rude and mean that the host's house gets more and more messy the more parties they have. Eventually, the house would run out of space to have any parties in at all. Cleaning up memory when you're done with it is important so that your program doesn't use up more of the system's space than necessary. Another problem ownership solves is that the owner of the dish is responsible for cleaning it up, not anyone else. If the host decided to clean up the dish while people at the party were still eating, that would be rude. You'd go to scoop another serving out of the dish and nothing would be there. That's like one part of the program cleaning up memory before another part is done using it. Let's contrast this with what other languages do. We're going to look at C, which does manual memory management, and Ruby, which has a garbage collector. In C, your code has to explicitly perform both allocation and deallocation. When you want space to store some data, you call malloc and specify the amount of memory you want. When you're done with that space, you call free to return the memory to the operating system. The advantage of this is that you have complete control over when your program allocates memory and how much it uses. This control lets you write programs that run quickly and take up the least amount of space. However, having complete control is also a disadvantage. C by itself doesn't prevent you from messing this up. If one part of your program calls free and then another part tries to use that memory again, that's called a use after free problem, and is like the host of the party cleaning up a dish while people are still eating from it. If you forget to call free once you're done with the memory, eventually you'll run out of space. This is a memory leak, and it's like bringing a dish over to someone's house and never cleaning it up. If two parts of your program try to clean up the same data, that's known as a double free problem and can cause memory corruption. This would be like the owner of a dish and the host both trying to clean up the same dish. There are tools to help diagnose and debug these memory problems, but the C language doesn't help us out very much. These problems happen a lot and have caused major security flaws and crashes in lots of different kinds of software. Just trying really hard to be careful hasn't proven to be a very robust strategy for software as a whole. Ruby, on the other hand, takes care of managing memory for you and has a component called a garbage collector that runs alongside your program cleaning up memory that you're done with. The advantage of a garbage collector is that while you're writing code, you don't really have to think about managing memory at all. The garbage collector keeps track of which memory is still in use and cleans up any data that your program is done with. You also can't have any of the problems we mentioned with C because Ruby is taking care of all that for you. The downside of using a garbage collector is that you lose control and performance. When it runs, the garbage collector takes up computing resources that your program could be using. Your program will also likely use more memory than it strictly needs because the garbage collector only cleans up memory when it's sure you're done with it. Rust is trying to get the best of both worlds here. Ownership gives you control over memory allocation and the associated performance, but by cleaning up data automatically when the owner goes out of scope, we can't mess up the memory access and we won't be using memory longer than we strictly need to. Let's get concrete with ownership by using strings. A string is a type that has data that needs to be cleaned up when it goes out of scope. A string value tracks how much space is allocated, how much of that space is used, and the UTF-8 data. When the owner of the string value goes out of scope, the UTF-8 data needs to be cleaned up. There are a bunch of ways to create a string. One is by using string from. This code creates a new variable named a and sets it to a new string instance by allocating memory which holds the text hello. We can use the a variable, such as by printing it out, until the closing curly bracket of the main function. At that point, a goes out of scope and the data allocated for the string gets cleaned up. We can modify the string data by adding more text to the string. The variable needs to be made mutable, and then we can call the pushStir method on a and give it more text. This will allocate more memory if necessary, and when we go to use a, it will have hello there in it. By default, with non-primitive types, Rust moves ownership. If we have the variable s holding a string, and we create a new variable t and assign s to t, this will move ownership of the string from s to t. Afterwards, the variable s is no longer available to be used. We've shown moving ownership in the context of variables. Now let's bring functions into the mix and see how moving also applies to them. Here's a function named say that takes a string as a parameter and prints it out. This is different from the previous example where we did this in the main function. When we call the say function with a as the argument, ownership is transferred from a to s, and the string data gets cleaned up at the end of the say function. We can verify this by trying to use a again after calling say in main. Here, we try to print it out. If we try to compile this code, we'll get an error that we're not allowed to use a because it's been moved into say. We can also transfer ownership out of a function by returning a value. Here's a function that doesn't take any parameters but returns ownership of a string that contains the heart eyes cat emoji. Memory is allocated in the heart eyes cat function, but it isn't cleaned up there. Ownership of the memory is transferred to a, and the memory is cleaned up at the end of main when a goes out of scope. What if we wanted to keep ownership of some data, but needed to also give ownership of the data to another piece of code? We can do that by cloning. Cloning makes a deep copy of the allocated memory. Then there will be two copies of the data that each have an owner, and each owner is responsible for cleaning up their data. Cloning is one way to get around errors having to do with moved values. You may end up allocating more memory than you strictly need to, but you'll be allowed to do what you're trying to do. As an example, when we wanted to use a again after transferring ownership to the say function, we can call clone on a and transfer ownership of the clone to the say function instead. This code compiles and runs. The clone data gets cleaned up at the end of say, and the original data gets cleaned up at the end of main. It's time for you to get some experience with strings, ownership, moving, and cloning by trying this exercise. Your task is to implement a function that turns words into their plural versions by adding an s to the end of the word. In main, you'll have a string like book, and your goal is to get main to print, I have one book, you have two books, by calling your pluralize function. Note that the string type has a method called pushStir that you might find useful. It's not the only way to complete this exercise though. If you get compiler errors while working on this, or if you get stuck, that's great. In the next module, we'll be going through some of the problems you might run into while working on this exercise. Now you've learned how Rust's ownership differs from manual memory management and garbage collection, as well as the basics about string. Apply what you've learned about moving and cloning as you try the exercise before the next module.
If you're enjoying this video, you'll be glad to know that it's just a small part of a much larger course that can be found on Manning's liveVideo platform. liveVideo is host to a variety of courses for software developers and engineers, and features helpful tools like our interactive transcript and intuitive integration with our live books. For this course and others, visit livevideo.manning.com.